Assalamualaikum and very good afternoon. My name is Wafidin bin Abdul and I am from Group A. And today we are going to present nanotechnology in gas treatment and processing, which focusing on how nanoparticles improve gas separation, dehydration, and also CO2 absorption. Next is table of content. Today we are going to present the introduction, key concepts, challenges, current industry practices, new technology and case studies, and also the conclusion. So for the introduction, nanotechnology involves the use of materials at the nanometer scale, which is the range from 1 to 100 nanometer, to enhance the physical, chemical, and also mechanical processes. In gas treatment, it is used to improve the efficiency of gas separation, dehydration, and also CO2 absorption. And what is its relevance to gas engineering? Firstly, gas treatment is a critical step in natural gas processing to remove impurities. Why it is important? Because nanoparticles offer superior surface area, selectivity, and reactivity, making them ideal for more efficient, selective, and cost-effective gas purification. And nanotechnology is applied on gas separation for 20%, and gas dehydration 15%, and CO2 absorption for 25% for the case studies that has been applied. And that is all from my part.
Next, for the part key concepts and principles, move on to the role of nanoparticles in gas treatment. So first, we need to know what are nanoparticles. So nanoparticles are tiny particles that less than 100 micron, and then it has large surface area, which means that it has more reactive site to do a chemical reaction, and it is a tolerable surface chemistry. So move on. What is the concept of nanoparticle in gas treatment? So I divide it into three types of process. First one is gas separation. So for the gas separation, nanoporous membranes allow selective gas passage. For example, material organic framework membranes for carbon dioxide and methane. Next process is dehydration, which is commonly used silica nanoparticles. So these nanoparticles will attract and trap water molecules. It is more efficient than glycol on this system. So the last one, the process is the CO2 absorption. So material of framework or carbon nanotube provide high affinity binding for trapping gas. So it is more faster and more efficient for CO2 capture.
Yeah.
So moving on to challenges, although nanoparticle can increase the carbon dioxide capture, gas separation, and also the dehydration, but it also have challenges. The first one is the environmental and health risk, where it is potential toxicity and environmental pollutant, where the nanoparticle will enter the soil or water, which posing risks to the ecosystem and also human health. Their small size allow them to penetrate to the biological membrane. The second one is the economical and scalability, where the nanoparticle is mostly costly and also resource intensive, and the scaling production while maintaining quality and performance is non-trivial. So the high cost of this material can be a barrier to the commercial and also in large-scale industry gas treatment processes. And the last one for the challenges is the technical and operational issues, where incorporating nanoparticle into membrane and absorbent often lead into pore clogging and also agglomerate. And the second technical issue is the trade-off between the selectivity and also permeability, where in gas separation, improving selectivity often reduces permeability and vice versa. This fundamental of the trade-off still limit the effectiveness of many nano-enhanced membranes. And the last one is the deactivation over time, where many nanomaterials lose their efficiency over time, and chemical degradation and also structural will collapse during the extent of the operation.
Next, I'm Yosoni. I will be presenting
think about the current industry practice for removing CO2 and N2 from natural gas based on the review by Raffel et al. 2012. So firstly, for membrane separation is becoming a more common thing, especially for CO2 removal. These membranes are compact, modular, and well suited for offshore or space limited, so they are often used in upstream of LNG trains. Next, for nitrogen removal, industry use pressure swing absorption (PSA). A well-known system is a molecular gate which use material like PTS4 to selectively remove nitrogen gas based on molecular size and speed. This either for the small scale or remote gas fields. Next, for the amine-based absorption. Amine-based absorption is the industry standard for CO2 and H2S removal. Chemical like NDEA or MEA is used to absorb the acid gases in tall contact column, then release them in a regeneration unit so the solvent can be reused. And finally, for the cryogenic distillation, is the main method for removing nitrogen gas in large-scale LNG plants. It separates gases by cooling them down to a very low temperatures, although it provides high purity, but it's expensive and energy intensive. So in summary, for the current industry practice, the technology chosen are based on their plant size, gas composition, and the economic factors.
Now, so let's move on to the new technologies in nanotechnology. First is the nano adsorbent for CO2 and H2S removal. So this technology uses nanomaterials like carbon nanotube, graphene oxide, and metal organic framework as highly selective adsorbent. And their advantage is the higher surface area and tunable pore structures that lead to a greater selectivity, capacity, and faster absorption rate. Next is the nanostructured membrane, where the technology is in the integration of nanoparticles such as silica and zeolite into polymeric membranes. And their advantages is it enhances the permeability, chemical resistance, and anti-fouling properties. And finally is the nanofluid in gas processing. The technology uses fluid that contains dispersed nanoparticles to improve the thermal conductivity and reaction rate in absorber and stripping unit. The advantages is to improve heat exchange in absorption, regeneration cycle that leads to lower energy consumption. The first case study is in South Pars, Iran, where they use the gas sweetening with CNT membrane. So, carbon nanotube membrane, also known as CNT, are advanced materials designed for gas separation. These membranes consist of ultra-thin cylindrical carbon nanotube embedded in polymeric matrix. Their unique pore structure allows gas molecule like methane to pass through rapidly while effectively blocking carbon dioxide. The application is when used in South Pars. The application of this nanotechnology is used in South Pars for gas processing plant to sweeten the natural gas by removing carbon dioxide, to increase the methane purity, to prevent carbon dioxide corrosion in pipeline and liquefaction units, and to comply with the LNG and pipeline gas specification. The results of this technology is it enhances the gas quality and reduce the methane losses. Nanotube strength and stability reduce the degradation and replacement frequency. CNT membranes are less prone to clogging by particulates or liquid contaminants, improving the operational uptime and reducing cleaning downtime. So the second case study is in Alberta, Canada, where they use nano catalysts for sulfur recovery. These are nano-engineered catalysts composed of cobalt, molybdenum, and supported on gamma alumina. The nanoparticles have very high surface area and optimized active site, allowing them to accelerate the Claus reaction used in sulfur recovery units. The application of this technology is used to treat sour gas streams by converting hydrogen sulfide into elemental sulfur, reducing harmful SO2 emissions, complying with environmental sulfur regulation, recovering valuable byproducts sulfur from natural gas processing. The result from this technology is it achieves near complete H2S conversions, meeting strict environmental standards. Less energy is required to drive the reaction and extending the equipment life. And finally, it reduces the heating demands, leads to lower operational costs and carbon footprint.
Go on.
So the last part is the conclusion. So first one is nanotechnology enhances gas treatment through improved efficiency, selectivity and environmental performance. Second one is advanced nano-absorbent catalysts and membranes enable better CO2 capture, CCUS, contaminant removal and gas purification. Third one is offers potential for cost-effective and sustainable gas processing at industrial scale. The fourth one is the key challenges remain in terms of scalability, material stability and implementation. And the last one is continued research and innovation will drive wider adoption and real-world application in the energy sector. That's all for our Group A. Thank you.